Okay.
Right. Good morning, everyone. Today we will start our sections on data analysis. My topic is going to be on solution sketching of biomacromolecular complex. And so I think I don't know how much you have experience with sense data, but when I was preparing the material, I thought that what should be the steps for uh, do the data analysis and from where we started, right? So let me share my screen and okay. So from where we started with the data analysis, and today some topics that we're gonna be covering during the data analysis, the Guinea analysis for biomacromolecules, PFR calculations, that which is the part distance distribution, crackle plot to estimate conformation, detect conformational changes, estimation of the molecular mass, and also using atomic structures of PDB models to fit the experimental data. And some you'll be also focused on the softwares that we generally use to analyze those types of data. I hope that I can cover that in 45 minutes. I'm going over some details of how the approach that we use and the resource that we have. And also in the hands-on section, we can be more like free uh, to go over the data and can go over one by one and check how the person is analyzing the data and how what information is getting from there. I think that is the more and also, if you have any data that you want me to have a look and have some guidance how you should analyze, also gonna be the opportunity for you there. So now, the resource for us to analyze SUNS data, uh, there is a couple of them are available, and then we can start with the most common softwares that we have access to analyze the data that we collect for solution scattering. Start for HTSAS, which is the most common package. It's very useful for analyze also SACS data. And at least here's some softwares that is very common on, and you can apply the SANS data and SACS data as well for both cases. But here's the ones that they are developed to help you analyze the SANS data. And start with Cryson, that's going to give you the ability to fit PDB models to our experimental data, GNOME to calculate participant distributions, SAXHEF that is going to help you to do modeling, rigid body modeling, and can allow you to use contrastive variation series and also including SAX data. If you have a mixture, you can use oligomer to try resolve this mixture of the different species that we have in your data. Damming and DMF can be used to do ab initio modeling, so you can uh, calculate a low resolution envelope for molecule of interest. Gasbur is more like a chain-like model of your protein. So basically, you assume you have a chain sequence of residues, and then you can propose um, some kind of conformation that is chain gonna assume based on more data. And Monza, you can do ab initio phase if you have different contrast points, and then you can combine those contrast points and then do an ab initio model for each part of the complex. If you have a doctorate complex, you can use Monza to try see the conformation of individual subunits within the complex. We also have, in case we have a disordered structure, you can use ensemble optimization to see how it looks like the ensemble. And if you want to do superposition of the PDB models with any of those models that are generated here, you can use supercomp to do the comparison or the superposition of two structures. All of these softwares, they are in a suite of softwares, which is the HSAS spec page. It's if you don't want to have access, you don't use often, then you can also use the online version of HSAS. I recommend to have both in the computer, and sometimes you want to do some kind of demo thing, then it's going to take longer to run. You can definitely go use the online version. It's going to run on server, and it's going to send you one email to you, say the job is done, and you can retrieve your data from there. uh, for You can also do data manipulation using HSAX, uh, subtraction, scaling, merging, those kind of regular um, process that we do after you have the data collected. Here in the second topic we have BioSax Raw. It's a software developed to analyze Sax instance data as well. And it's very useful to do background subtractions, scaling. Uh, Raw also have the ability to do the Guinea analysis there, uh, as well as those it sucks. And all of the softwares in general, they have a software or uh, kind of macro. They allow you to do those analysis very easily, so it's very handy. And Raw called the Genome, which is the software that does the PFR calculation from 8 them have to do a Benito model, and Dense, which is the was developed for Thomas Graham to do uh, a Benito modeling using a different approach than those DEMF. And also we have Scatter, which is another uh, option for analyze data, and they are kind of similar of the feature they have. Depend of how do you like them and how do you want to them. I personally like to use Raw. It's my preferred software to do data analysis. And the second one here is resource that we have is the where you can from where we can get structures to do comparisons with the or experimental data, right? I think the protein data bank PDB is the most common version, common resource that we can have. We can easily search for a protein structure there and get the PDB, but also have the cryo and NMR structures that can be used, not only crystal structures. And now we are more towards to for those structures that can't fold. They are uh, they have a fold on they fold on the on solution on they are not like disorder. We can use AlphaFold, which is the was has been developed for a while, but last year they really improved the ability of the precision how the AlphaFold can predict one structure. So for data visualization, we have PyMol and Chimera. So yesterday I got some questions about PyMol is not free. There is a student version you can use of PyMol. It's not really, you can use that student version to download and use PyMol. It's free to use for academic use. Chimera is the same for academic use. You can use a Chimera version. You don't need to pay the license for that. And if you want to compare Sachs data, for instance, you can also using the Fox Sachs, which is a web server that does fast calculations of Sachs profile. In general, you need to use those to, you have a probably have both data sets. You have Sachs instance, so you want to do comparisons with the Sachs. So today in my talk, I'm gonna over more here on bio Sachs raw and how you analyze the data. Please feel free to have any questions. I don't see anyone now. Cannot see anyone. during my presentation, but let me see. Feel free to stop me and ask any questions. So in terms of what we saw yesterday and my talk on some preparation, the desired sample that we want to is a monodisperse sample uh, that we can extract all the information that we can get from solution scattering experiments. So we can calculate mainly the intensity over Q. The is gonna give you the scattering profile, how this the scattering the behavior of the scattering profile. We will look for samples that were low Q level off here to a flat line in the low Q, so we know that we have a nice Guinea regime to analyze, and I'm going to explain more what is this good Guinea regime and what is the conditions for you to have this Guinea regime. So basically you have a flat line in the low Q, so you can from here you can directly extract uh, the I0, the forward intensity, and determine the molecular mass, which is proportional to the I0 is proportional here to the number of particles, which is included here in this case the concentration. And we are in dilution conditions, so no structure factors. It's present in our data. And then we can, like I say, extract the rates of gyration, the low Q. We can determine if you have a more globular or extended structures, or even is not really is not fold is disordered. So we can determine the conformation of the structures. The oligomerization state, the state is also determined using the scattering profile, because if you know the molecular mass, we can, and if you know the molecular mass of each subunit, we can determine the molecular uh, vague. And comparisons, like I say, with PDB structures, and now we have of a fold again, which is give us a great ability to almost, if the protein is folded, we can calculate PDB structures and starting the modeling for there. Uh, and you can also do calculate the molecular envelope, which is give you one idea of the overall shape of the molecule. So let's start from the beginning. Let's assume you have data. You collect the data here. I'm show protein sample data. The data that we collect here is for HSA. Um, the way that we do the experiments here, we in general we collect our we do the calibrations first, and then you're gonna for proteins we have some standard configurations like Venk said yesterday, where you can already use those already calibrated configurations to do the war experiment. And in this case here, this sample was collecting using 15 meters 6 angstroms. Uh, but ideally for proteins of that size, you can use the 7 meters 6 angstrom configurations and get good signal to noise as well. In this case here, my sample, I did not subtract my empty cell during the data reduction, because I was want to show for you how it looks like the data before and after empty cell subtraction. Uh, and here we have the scattering profile of our sample, which is the orange, and then the blue is the scattering profile of my buffer or solvent. And then in the red, I have the scattering profile of my empty cell. So there is a correction that we can do during the data reduction. Basically, we assume that sample and buffer, they both are samples, and you subtract the empty cell there. But you can also subtract reduce the empty cell separated and do the subtraction afterwards. So here we can load and raw. This is the raw interface, by the way. When you load this there in raw, We have the ability to do subtraction of both buffer and empty cell, the background subtraction here, for, assuming that we are subtracting against the empty cell, which is my third item here on my list. And then I'm do the first correction necessary to analyze my data. So that is the first step, the basic first step for you to move towards the data analysis. So you start removing the backgrounds of our data. So you are doing the necessary corrections for you to have the sketching profile. So if everything is fine, in this case here, everything is fine. I do one-to-one. Um, After I intentionally scale a little bit up the empty cell that we're gonna work, so you can play with the scaling, and I'm gonna show how to do that on raw on the hands-on section. And after you already subtract the empty cell, and then you have the, now I'm loading here only the subtract empty cell data. You have your buffer. You see no scattering is a flat line, so you don't expect to see a large amount of scattering from of our buffer. And you have our sample scattering very well here. All they need to do is subtract the sample minus buffer. In this way, you remove all the backgrounds that you need to remove, and you are getting up just the sketching profile that you're gonna use to analyze your data. All right. Okay. So that is the two corrections that is necessary. Uh, yes. Okay, so now how we do Gini analysis, right? Is we have our data is the first thing you do in general when you are run or bin time and you are collecting our data. So basically, after you have our data subtracted, you have our sample, you have this scattering profile of our sample already subtracted. The region of the interest is the local region. That is the data range or the key range that we have to looking for. And like I said, so the data cannot be turned up in the local because that is you have suggestion that we have aggregation in your data. So the way that raw just called the the Gini analysis, you could do a right click with the mouse uh, on the where sketching profile is gonna pop up to this window for you here. That is gonna show you the Gini analysis window. Is there where we need to work with? So this is a real sense data. So we are looking for the what should be looking for you exactly how you collected data. So here we are collecting the RG and I0 from the Guinea. Uh, so the Guinea analysis, like Volker said yesterday, is approximation of the scattering at the low Q, the exponential decay that the scattering have in the low Q. So and you are determining the radius of gyration and the I0 of this approximation. So you linearize this equation here, applying the logarithm, and you have the logarithm of the IDQ by the Q square. How you analyze this plot here? Basically, what you expect here for a good linear fit is you have a straight line fitting. You see that when you have those kind of war data, the residue of the fitting, it's randomically distributed across the zero line here on the normalized residue. And then you say your word sample is mono-disperse. You not you not see signals of aggregation. What happened when you have aggregation? This shape of the curve becomes a huge shape, like a smiling shape. And then you can say that what aggregation is maybe to have or the upturn here in the Guinea plot is very severe, like I showed yesterday as well during my talk. So that is tell you that the sample it's not monodisperse, it's have some degree of aggregation, and depend of the level of aggregation, you cannot really analyze the data, but it's not always the case. Like I'm going to show you, you can do some comparison with crystal structures and see how the overall profile looks like when you do the fitting with your model. Uh, so what is necessary for you to have a good Guinea fit? So the reliable Guinea analysis for you is that your Q minimum that you are fitting your data, the Q minimum by your RG is not greater than 0.65. The same for the Q maximum by RG is not greater than 1.3. That is true for globular system, and for very elongated system like the long cylinder that uh, Volker showed yesterday, that not greater than 0.8. And the other parameters that we also try here to do is that for you have a good range of Guinea, so you are catching the number of points necessary for you to have confidence on the fit should be higher than 2. So greater than 2. And here what we get from the fitting is the I0. So the raw is going to give you the I0, the forward intensity for you. The uncertainty or real of your parameter is give you here in this tab below. And the radius of gyration, which is for this case here, it's 24.2 plus or minus 0.5, around 0.5, and give you the Q minimum and Q maximum. And also, the Q by RG limits is given for you here. As you see, way below 0.65 by my Q minimum by Q maximum, and it's not greater than 1.3 for the Q maximum by RG as well. Uh, During the hands-on section, we can play with this data and other data that I'm going to share with you, and then we can um, uh, see how the Guinea fits work in the real life. So next, we have here the Kraki plot analysis that is going to differentiate for us between extend and compacted conformations. So the Kraki plot analysis is also useful for you to do background subtraction. Sometimes the way that sometimes I do background subtractions, I use to plot the Kraki plot here data, and I started doing my background subtraction using this plot as my guide to know how much background I should go. So if you look at the insect plot here on the raw window, we know that for a fold structure, so the you have a bell shape for of the case of a fold structure, and choose scattering is gonna be go smooth to around 0.3, 0.4. In the high Q region, it's gonna be go to 0 in that area there. For unfold structure, it's gonna reach a plateau there because of the power laws that the scattering for a fold and not fold structure is different. So the Kraki plot can differentiate in the high Q is different. So the Kraki plot can differentiate um, um, both type of conformations. And you see some intermediate state with a partially unfold, how it should look like. So you can also do dimensionalis Kraki plot. So you are removed to dependence of the size of the protein. So you normalize by RG, and for a very globular structure like a sphere, so our dimensionalis Kraki plot is going to have a maximum of 1.1. The bell here is going to have a maximum of 1.1 at 1.73 Q by RG. That is true for all globular proteins. And if you start having deviation of this maximum here to or right side on the plot, it's mean that your systems become more flexible. So that is a qualitative information way to analyze your data, but it's very useful when you have different data sets and you want to compare them and see if you have conformational changes. Again, so this analysis is also available in raw. We do just do a right click with the mouse and we call the window here dimensional character plots. And for do the data analysis, for bring up this plot, you do a click right with the mouse and we're gonna ask to do the plot the data has a character plot. So now the part distance distribution, it's where we calculated the the most probability you find two particles in the space in the radius. So here is the data range that you're gonna cover. So in principle, uh, yeah, ideally, you use the entire Q range to use the P of R. So the P of R mathematically is a Fourier transform of our data from the reciprocal space to real space. So it's the conversion, so we can visualize the data on real space. And here what is the it's also give for us the conformation of our protein, how it looks like the conformation. It's more globular, is more extended. What is the state of the conformation of the molecule from the scattering profile? So when you do the P of R, so you can on raw you can play with the limits you want to do. In general, that is a truncation of our data. So you don't from the Fourier transform, you don't need to use the full Q range uh, to recover the P of R. You can use the Q range, which is going to give you the best fit. The PFR does not really use the full range. Ideally, you should use the full range of our data, but in some cases, if the high Q is to noise, you definitely you don't want to use the points. Or if the low Q is to noise, you want to avoid that the region as well. And here you have your control where you can fit your data on raw, and you can start playing with your demasking. Like I said yesterday, you can extend the choose region here to see if how is the behavior of our demaskment. If you have any issue to really get a good demaskment there, so war sample is not well behaved. Could be some issue on the background subtraction, could be some issue in the sample that you are not able to detect, but it's gonna be manifesting those problems in your data during the data analysis. And here is the comparison of what we get from the Guinea fitting, right? So we have our D maximum there, which is 82 angstroms for the sample here. And as a bit lower than that, I'm just extended to show that we can go a little bit further. And here we have the Guinea region, the Guinea fit that we did before. So we have the RG and I0. And here is the Guinea from the PFR profile. So the PFR profile also can give you this information of the RG and I0. So those are the steps that is the basically steps when you are doing solution scattering. We collect your data, we do the background subtraction, like I said, and we directly go to see the Guinea and PFR profile. They are kind of quality controls of our data, but also give the information that we are looking for in the solution analysis. And the information that is retrieved from the PFR is what Dmax, the RG from the genome, and the I0 from the genome. That we can always compare one each other. In some cases, those RGs does not match. That's case where the PFR give you a different answer. So it's not always they have to match one each other. You sometimes you see difference in those those values. Okay. Now, comparison with PDB structures. So here is the case where I use the PDB structures from the crystal structure of human cerebroalbumin at the HSA, and I retrieve this which is structure from the protein database, and now um, the fitting that I'm gonna look in here is that how the overall structure, my crystal structure, my models agree with my sketching profile. That is the main goal here. So we start with our low Q here. So the low Q, like I said, it's giving me the information about the shape, right? So if my low Q agree very well between my model and the crystal structure, it's mean that I have a good model to supply my data. So the crystal structure, whatever PDB model that I'm using, is well representative of the conformation that I have there. And then if you go to the intermediate Q range and the high Q range, here is more local information that we can get, so about the folding of the structure. So if you have smaller differences in the high Q region that does not agree with your sketching profile, it's mean that there's flexibility in your system that can be modeled. You can there's ways to use to uh, model just flexibility, allowing regions to be flexible, and you can adjust the high Q. Uh, so, and here I'm already loading raw the fitting of the HSA using the Chrysome. So this fitting was done using Chrysome. And you see the good thing about raw is also as well, you don't need to use another software to compile your data. You can load everything back again there. And it's gonna be raw is gonna be able to load your fitting profiling there. You can directly compile in raw. So the red profile here is the fitting of our HSCA data. I'm not using the full Q range to the fitting, so my kilo Q was too noisy, so there's no need actually to fit to our data. My Guinea region was defined um, around 0.06, so the fitting here in that region is already enough to capture the overall profiling. You see you have a very nice agreement between the crystal structure and the sketching this experimental sketching profile. This fitting I was using doing was I did this fitting using Chrysome, and Chrysome also report for you the RG of the model, which is similar what the RG we observed before for the experimental data, and also the chi-square of the fitting, which is very nice, very good. 0.85 is a good fitting. So we always want to get good fitting of our data. So chi-square all one is ideal. So we want to get a lower chi-square. So that is we also want to provide good models to our data. That is the main goal of doing those kinds of fittings. And if you want to do molecular mass calculation, so here we have the standard equation that comes from the uh, small angle scattering. So the molecular mass is proportional to the forward intensity, uh, the Avogadro number. We have divided by the concentration, and this factor here is the delta rho is the contrast, and ni here is the partial specific volume of the sample. And using this equation, you can directly calculate the molecular weight. So the I0, again, you're going to be starting from the Gini analysis of the part distance distribution. And concentration is something that you can measure during the experiment. So you need to know what is the concentration of for sample you are mentioning. So here, this table, we can definitely share this information if you so how it's just multiplied the terms on the numerator and multiply the terms of the denominator, and you can get the molecular weight of your protein very nicely. So the tricky part here is that you need to know the scattering length density of your protein in the condition where you are. So let's assume I'm 100 parts of the 2O, so my scattering length density of the solvent is 6.36. But if you want to know what is the scattering length density of our protein in 100% of the wall, I paste this table here, which is give you the percentage of the two and the scattering length density of a mixture of, in case of here is the water, you have you have a mixture of D2O and Ag2O, and you see how the scattering density change. And here is for our protein in that the scattering density of our protein that giving a buffer condition. So that is going to give you the delta rho, which is the contrast difference. So it's very easy to use. And then the partial specific volume is going to give you is a constant that is retrieved from literature. It's almost identical for all proteins, and you can use and you can get a nice molecular weight of our um, protein here, which is agree with the HSA. Now, my last topic is the how we build the envelope for a macromolecule using ab initio modeling. So basically, its job is doing using DEMF and DEMF. So you're gonna recover your ab initio shape is a BD model. So basically, the process is that you assume you have BD particles, them atoms in your system that is gonna be filling the same volume that is you have or some. So them if it basically mean the overall volume that you need to have to get the scattering profile, and using these them atoms is gonna look in the most probably all the ideal arrangement of these them atoms that represent the overall shape. So you retrieve this overall shape from them, and then you have to do a superposition of these coordinates, aiding for a PDB model with your ab initio model. And then SubComp is the software that does this kind of superposition for you, and it's gonna rotate your sample in different coordinates, and you see, sorry, you're gonna see which one is the best superposition, the best coordination of the both coordination of the structures of both ab initio and the crystal structure, and it's going to give you the best superposition of our data with our crystal structure. And as we see here for HSA, agree very nice. You have the good idea of the envelope. It's a low resolution uh, method, but give you a nice idea of the overall conformation and how you expect to see the conformation of our sample. And if you have obviously different conformations, you can detect those changes, see the overall shape of our sample. So I think pretty much is what I want to cover. That is just the last slide here is just like I remember from yesterday. So problems that is going to really corrupt our data in the analysis, which is going to be the aggregation that I already talked yesterday. I'm not going to be more so focused on that. And also, when you have the structure factor or repushing of our data, you see the Guinea here again manifesting those effects, those interparticles interferences in our data in the low Q. So we kind in data analysis, we are looking for those things. We ideally we want to work with a system that is no those types of effects. So there are any questions before I move in? So just here, just quick looking, we have is how the HSX looks like when you do data analysis. You have You can manipulate our data. There is the similar features here, and you can do also rates of gyration, P of R, and calculate the molecular weights using data sacks. Is a second source. Are there any questions? Hello.
No questions,
Okay.
Wellington, that I could see in the chat. Okay, we have one question. Feel free just to ask your questions, guys. I think there's not that many of you online. I think that was Lorena, was it? Lorena, is that you?
It's possible to mean them
Okay,
now.
I'll
Yeah, go ahead, Hill.
yeah, the question is it possible to determine the molecular mass of the polymer shell in a core shell? I think that would be tough, right?
Yeah, I'm thinking the conditions.
So I think you basically would need to know the volume occupied by the shell and the density of the polymer in that shell, and then you could figure out the mass from there. But I think it would be complicated. I think it would be hard to do that. I'm not sure you'd have the resolution and the measurement to get an accurate value. What do you think?
Yeah, I think the problem is the density, right? So
Yeah, you'd have to know that.
you
Yeah.
have to know density to the and the channel. Yeah, I can do a follow up on this question, but I believe definitely the issue maybe is it is the density. You know, you need to know the density. Definitely, you can recover the volume from the sketching, right?
Yeah.
But the density is gonna be the issue.
I think okay. I don't see another question right now. Well, I
So
think Lorena might
can't
be
you,
following up on that.
Wellington, can't you get
Yes.
the density by going doing the contrast variation, and so the density will be determined where you find the match point?
Would that come out of that, Gergely?
Yeah. So if you know the SLGs, right?
Yeah.
Yes. So the composition and the density and the match point will be three variables. And if you don't know only the density, then you can get it from the other two.
Yeah. But yeah, I think it might be a complicated calculation though, right? Because you would see, you need to have, well, there's volume, concentration, and then density are the three things you need to know, right? Let's follow up on that one. There's another question. Yeah.
Yep.
Maybe we can answer that offline. Can you see the chat, Wellington?
Yeah, just open. Yeah.
Yeah, Yuki has a question too. And by the way, guys, Gergely Nagy is an instrument scientist on the extended Q range SANS instrument located at the spatial neutron source. So Gergely is also an expert in small angle scattering. So Gergely, you should feel free to weigh in here and give your opinions. Okay.
Thank you. Thank you.
Yeah. So go ahead. Yuki has a question there.
If the molecular mass calculated from Guinea analysis is much lower than expected, What are some possible reasons? The first one that comes to my mind is that you are so I think I need to know some details. You are sure that your molecular weight is your molecular species a monomer or is a dimer? So you are made some assumptions, right, to assume that the molecular weight is lower than expected. So what are those assumptions? So in the case if you expect like a monomer, I would say they have some interparticle interference in your data. They were not accounted for. Is that the case?
Yeah, I'm not quite sure. It has been like consistently since our like previous sense experiment, our most recent ones, and the molecular weight is like consistently about like half than what we expected it to be a monomer species. Because the molecular weight calculated from Gilead is just half of that, and we were really confused like why that happened.
I think we'd have to have a look at your data, Yuki, to see.
Yeah. Make sure you have the right factors in your calculation as well.
Mhm.
So
Yeah, I think
that
we
is
can
a point.
discuss about that later as well.
Yes.
Thank you,
So
So the molecular weight, I guess, is less than what you would expect for a monomer
Yeah, that's right.
based on the amino acid sequence.
Yes.
Okay. Yeah, I think we'd have to have a look at your data to see what could be going on there.
Thank you.
okay. Any other questions? So if not, we can give a break now. Um, so we are supposed to be back um, at 10. We can give a 15-minute break. So that's gonna be 9. I think it's better give them more like 2 minutes, and then we can be back here 10:15. That's that right? No, no, no. 10:10. So we have 15 minutes break. Okay.